All right, let us start. So now we will start section 9.4, so-called absolute and conditional convergence. Okay, so let me write down. This is section 9.4, absolute and conditional convergence. All right, here is the definition. Uh, Definition for absolute convergence. A series, okay, an is set to converge, sorry, set to be absolutely convergent, convergent if the series an in absolute value is convergent. Okay. All right. Okay. An example of this is the following. Look at this series. Uh, minus 1 over n minus 1 divided by n fact n squared. Okay, this one. Uh, so an is just minus 1 to the power n minus 1 divided by n factorial, and hence square root of an, sorry, absolute value of an is just 1 over n squared, and 1 over n squared, this is convergent, by the p-test, because p is, sorry, 1 over 2 and less than 1, uh, so that the series an uh, is absolutely convergent. Okay. But look at this series. So this time an is minus 1 over n to the power n, and its square root is just absolute value is just 1 over n. Uh, we know that this thing uh, is the harmonic series, right? Is divergent, since it is the harmonic series. Harmonic series, and thus this thing uh, is not absolutely convergent. Uh, we will see that soon. We will see that uh, both series above are indeed convergent. Okay, so both of them are convergent. The first one is also absolutely convergent, and the second one is only convergent but not absolutely convergent, right? This will turn out to be convergent and absolutely convergent, and this one is convergent but it is not absolutely convergent. We will show that both of them are convergent. The first one actually is a consequence of the following theorem, which tells us that if a series is absolutely convergent, then it is convergent. If a series converges absolutely, then it is convergent. Okay. Now let's see the proof. And we have seen above that the converse is not true, right? We have a convergent series which is not absolutely convergent. This one. This is convergent but absolutely not absolutely convergent. And we will show that it is also convergent soon. Okay. Proof is as follows. So let an be a series which converges absolutely. Okay, let's see. Then, of course, this is convergent. All right. Now let Bn to be this gadget, An plus absolute value of An. Well, An plus absolute value of An is what? This is 2An if An is positive and 0 if An is negative, right? Hence, we have this. Hence, we have Bn is never uh, negative, right? Bn is never negative. And this is less than always uh, sorry. Yeah, this is less than 2 times An. Okay. Well, An is convergent since absolute value of An is convergent by the comparison test. Comparison test. This is convergent because this is a positive sequence. 2 times An is a positive sequence. Bn is less than this, and this is convergent. Therefore, this one is convergent. All right. But then uh, we have this. An is equal to An plus absolute value of An minus absolute value of an, which is just, I can write it this way, this is bn minus absolute value of an. This series is convergent. This series is convergent. Therefore, the difference is convergent. Since both bn and this one are convergent, uh, this is convergent. Okay, sorry. It's convergent. So this one, which is just bn minus absolute value of an, is convergent. Okay, okay. Okay, let me stop here. Maybe I do one example. Okay. Uh, okay. I think I can stop here.